Good afternoon, everyone. Myself Sana Sheikh. I'm a fourth year PhD student at IIT Bombay, and I'm taking a NPTEL live session of the course which is entitled as Symmetry, Stereochemistry and Applications. And the course instructor is Professor Anshuman Roy Chaudhary from ISL Mohadi. So we have already done 7 classes. So today is week 8 live session, and in live session we are going to discuss the previous year questions. So in today's class we are going to discuss the reduction reactions. So without wasting time, let's start the session. Yes. So before going to the question, I would like to give a brief introduction about the different reducing agents. So here the reaction is given here: preparation of alcohols by reduction of carbonyl compounds. So as you can see here, we have carbonyl compound and we have shown here reduction. So different reagent will act how in this case. So here you can see that when we have aldehyde, so the R dash is equal to H. In case of aldehyde, this R prime will be H. Okay. So in case of aldehyde, La it could be reduced by all the different reducing agent like lithium aluminum hydride, sodium borohydride, ranite nickel, palladium charcoal and dibyl H. All these reagents can reduce the aldehyde here. If we have aldehyde, then it can be reduced by all these reagent which is given here. Okay. But in case of ketone, again all these reagents are able to reduce them. You can see here the green tick, which means these reagents are suitable for these type of functional group reduction. So when we have aldehyde, that time all the different reducing agent can reduce it easily. While we have the ketone, also it can be reduced by LaH, sodium borohydride, ranite nickel, palladium charcoal and dibyl H can reduce ketone. Talking about the ester functional group is reduced by only the specific reducing agent. So here we will discuss here in ester could be reduced by lithium aluminum hydride because LaH is the strongest reducing agent. So as you can see here, all the different functional group can be reduced by LaH here, right? So talking about the sodium borohydride is less effective compared to the LaH. So that's why ester reduction of ester cannot be done by sodium borohydride. Ester can only be reduced by LaH, but also it can also be reduced by dibyl H at higher temperature. Because at lower temperature dibyl H reduces only aldehydes and acid chlorides. So at higher temperature only dibyl H can reduce the ester also. And here is a difference. At high temperature dibyl H reduces the ester into alcohol, right? But at lower temperature dibyl H reduce ester to aldehyde. That's the difference. So if we will do minus 78 degrees Celsius with dibyl, so it will give aldehyde from ester. Okay, and at lower temperature at higher temperature it will give alcohol. Let's talk about the other functional group, acid. So as you can see here, acid also can be reduced by LaH because LaH is strong reducing agent. Okay, and dibyl H also can reduce it at high temperature. But acid can also be reduced by BH3, which is not mentioned here. This is also a reducing agent and can reduce the acid, specifically acid. And ester specifically can be reduced by AlH3, aluminum trihydrate. Okay, specifically. So here, because today we are going to discuss a few questions which don't have these type of question, which include ALH3 and BH3. That's why I have not included here, but this is for your information only. Okay. Now, as talking about the acid chloride is very labile, so it can be easily reduced by sodium borohydride, so double H and LAH also. But Rani nickel and palladium charcoal are unable to reduce acid chloride. Palladium charcoal is mainly used to reduce double bonds. Okay. I hope these reagents are clear to you. Let's move to the question now. So here we have the first question. Predict the product of the following reaction. So as you can see here, HBr we have. So this double bond will take up the proton here, right? And it will give you a carbocation formation. So which carbocation is more stable? So if we have different substituent on the double bond, that time we can consider the carbocation stability. But here, because both the carbocations are secondary here, so both can be formed in this case. So this is called a Markovnikov rule. Markovnikov rule, where the carbocation stability decides the major product. But here, because we have both the carbocation secondary, so that's why both will give the product. So first, if carbocation formation will take place, then Br- will act as a nucleophile and trap the carbocation here also. But if you will see that we have here methyl position fixed on wedge, right? It is on a wedge, so that the attack of nucleophile can be occur either from the bottom side or from the top side, right? But because methyl is top side, so the bottom side is will be bottom side attack will be more favorable. But still, because methyl group is not that much larger group, so it won't affect that much. So that's why we will get here four different types of product. You can see here, in this case bromine is coming from the top side, right? And in these two cases it is coming from the bottom side. So that's why we will get here four different products. We can say slightly these two are slightly major because of carbocation stability. Sorry, not carbocation stability, because of the methyl here, and it will create a little hindrance from the top side. So the bottom side will be more favorable compared to this one. Otherwise, you can make a chair conformation also, and you can easily find out it here. Suppose we have this chair here, and methyl is on this position, correct? And one carbon, yeah. In what I will draw both the cases here. In this case we have carbocation here, and the other case we have carbocation here, correct? So because it is top side, so it can be comes from the equatorial position also, from axial position also, right? Wait, I will draw here clearly. Carbocation and carbocation. Okay. So because it is at equatorial position, the coming nucleophile can come from this equatorial position also, from top position also, right? Here also the same thing. It can either attack from top position or bottom position. That's why we will get all these stereo isomer in this almost same ratio. Okay, so this is the product we will observe in this case, these four different types of products. There is one more possibility we can see here, when the carbocation formation will take place at this secondary carbon, right? But this hydride wait okay, so this is the hydride which can be transferred here to make a more stable carbocation. So here hydride transfer will take place and carbocation will generate over here this carbon. And all of you know that tertiary carbocation is more stable than secondary one, and secondary carbocation is more stable than the primary one. So this is the tertiary carbocation which is more stable compared to this one. That's why this one will give the single product, where you can see that bromine will trap the carbocation from the bottom side, because that's the only side which is available. So after the carbocation formation, not the stereochemistry will get destroyed, right? And bromine will trap the carbocation. So here only one stereo center is there, so there is no Dr, and we will get our desired product. Next question. Yeah, this is also a similar question, but only difference is here the double bond is here in this case alpha beta unsaturated, and here it is uh, on double bond is on tertiary carbon also only. This is quaternary center. Okay, so here again the same thing, it will form here. What will happen? Carbocation generation takes place. In this case, now the carbocation will form only here, because this is a tertiary center. If carbocation forms here, this is not that much stable. So because of this tertiary carbon available here, carbocation will form here only, tertiary carbocation. And after the carbocation formation, this Br minus will trap the carbocation. So here in this is secondary carbocation which will form in minor because of stability, and this is the major one. Okay, and it will give two different product but in different ratio. So this will always give you a major product. This is minor, and this is follows the Markovnikov rule equation. Okay. I hope all of you are clear with this question also. Next, predict the product of the following reactions. As we have discussed in earlier classes also, and today also we have discussed different reducing agents, right? So in today's class, when we were discussing the different reducing agent, we have discussed LAH, NaBH4, palladium charcoal, dival H, right? And we also saw that the sodium borohydride, this sodium borohydride can reduce, anybody, anyone? it can reduce only aldehydes and ketones. Am I right? Right? But here we have two functional groups. One is ester, one is ketone. So all of you know that NaBH4 can't reduce the ester, so we will get the product which have only alcohol here, and ester will remain as it is because only ketone reduction will take place. So how many of you are aware of the mechanism of this reaction? Okay, we will discuss. So how it works? Reduction of aldehyde and ketone, how happen? Here we will discuss. So first of all, the sodium borohydride will attack on this carbonyl center because this is a electrophilic center, right? Electrophilic center where hydride will attack H minus, okay, and it will form a is an intermediate like this one, okay, and BH3 will knock out. After this one, the next step is a protonation. So how the protonation will take place here? This is a water molecule. So after at the time of workup, when we will do the workup, this O minus will take up the proton and O minus will knock out, and O minus and will be stabilized by Na plus ion in the system, okay, and we will get the secondary alcohol as a product. So here, in this case there are two steps. First the addition of hydride ion and followed by the protonation to get the desired secondary alcohol as a product, okay. Now let's talk about the next question. Yeah, all of you are thinking this reagent we didn't discuss, right? So I will tell you how to think about the reagents here. Okay, so here we have lithium aluminium tetrabutaoxyhydride. So this is similar to AlIAH4. Am I right? In lithium AlH4, all the substituent on aluminium are hydride. But in this case, what is the other substituent? Lithium will remain as it is, aluminium. One is H, hydride, right? Other three groups are O, third butyl. Okay, so this is the reagent. So all of you remember that here there are four hydride of in aluminium tetrahydride, lithium aluminium hydride, and in this case only one hydride is there. So in all the other substituent are also available. If you will see the reducing agent, in all the cases LAH is more reactive compared to all the reducing agent. Always remember this one, okay. And reducing agent which include aluminium are always more reducing agent, more stronger reducing agent compared to sodium borohydride. Remember this one, okay. Now all of you can say that sodium borohydride cannot reduce some part of the molecule, but LAH can reduce all those things. And for specifically reducing some selectively reduction, we are using different types of reagent like this one. In this case, here the reduction of ketone is taking place if we will use here NaBH4 or ALH. Sorry. Okay, sorry. Lithium aluminium hydride. What we will get here? Alcohol, secondary alcohol. But to get the aldehyde, we are using this lithium aluminium terbutaoxyhydride reagent. So we will discuss the mechanism, then it will be more easy to understand. What happens here? Okay, so here mechanism: reduction of acid halide by aluminium, lithium aluminium tributoxyhydride. Here the first of all addition, instead of the acid chloride, here we have ketone. So I will write here CH3. CH3. Okay. So here this hydride will attack in first step on this carbonyl carbon, correct? And we will get this as an intermediate. After getting this intermediate, what will happen next? This lone pair of oxygen will push over here and the CH3 group will knock out. So breaking of this CH3C bond will take place to give the corresponding aldehyde as a product. So because this reagent can transfer only single hydride, it will not give you the over oxidized product. Instead of that, we will get the aldehyde as a product. So here in this question there is a mistake. Don't consider that CH3, here Cl is there. In question, this is a mistake. So if we will reduce it by sodium borohydride or lithium aluminium hydride, we will get primary alcohol. Okay, but here because we have the different reagent, it will stop at aldehyde because this reagent can transfer only a single hydride. But lithium aluminium hydride and sodium borohydride can transfer 4 hydride. That's why the reaction won't stop at this step and it will further undergo hydride transfer if we will have other reagent. Okay, that's why I specifically chose this reagent. So hydride transfer will take place and it will give alcohol, but in this case it will stop at aldehyde position. Okay, aldehyde step. Next question. Predict the product of the following reaction. So here sodium sorry so here lithium aluminium hydride is used for reduction of amide. What is this functional group? It is called as amide, right? So remember, amide can be reduced by LAH. Okay, can be reduced by LH, but sodium borohydride cannot reduce amide. Okay, so here we have lithium aluminium hydride which can reduce the amide at 0 degree in dry ether. So followed by methanol. So here we will discuss the mechanism, what happens exactly. First of all, in amide case, hydride transfer will take place. Our first step is hydride transfer to carbonyl in all the reducing agent. Hydride transfer reaction. Okay. So first of all, hydride transfer will takes place to give this intermediate. Now you can see this lone pair of oxygen could bind with aluminium, and it will give the intermediate which will look like this one. Okay. Then lone pair of nitrogen will push here, and this group will knock out. Okay. Why the lone pair of nitrogen only pushes here, and why S3 cannot bind with nitrogen? Because of the different energy of the orbital. So because the lone pair of nitrogen are higher in HOMO compared to the oxygen one, and it is more easily available to donate, that's why it will push the lone pair of electron here, and it will get knockout. Okay, to give this iminium ion. After getting this iminium ion, then again the hydride transfer will takes place from lithium aluminium hydride to give the primary amine as a product. Okay, so I hope all of you understood. Next, yeah, predict the product of the following reaction. As I told you initially, BH3 can also use for reducing the acid group, but here we don't have acid, right? We don't have acid. Now what's the role of BH3 then? BH3 will add on the double bond as on the basis of Markovnikov rule. Okay, what is the Markovnikov rule? Stable carbocation, or we can don't say stable carbocation, or we can say that the more electrophilic group will always, in case of HBr, suppose we have HBr, right, and this is a primary carbocation and this is a secondary one, right? Suppose I'm just taking one example. So here in this case, carbocation stability will form here, right? This carbocation will be more stable. Suppose we have double bond here, right? Right. But in short, we can also say that the this is electronegative compared to H1, right? H is electropositive, Br is electronegative. So this managed charge species will always take the secondary carbon. Okay, on this side. So in this BH3 case, in BH3 case, we will split in BH2 and H, right? It will attack like this way. So H, and in BH2, BH2 is more electropositive compared to this one. Okay, so because electropositive will always go on less substituted carbon, right? So that's why this BH2 will come over here, and this will go here. Okay, that means carbocation generation will take place as here, because tertiary carbocation is more stable. All of you know that tertiary carbocation is more stable. Suppose I am here making tertiary carbocation, correct? So here BH2 will come because of less electronegativity, higher electropositivity. Okay, and then it will trap the H minus to give the product this way. Got it? This is the product. After getting this product, in next step what will happen? H2O2 will give the OH to make the alcohol. So we will discuss the mechanism first. We will discuss the mechanism here. how it works. The oxidation step, first step is the oxidation step. The second step of the hydroboration reaction is an oxidant. So till here all of you are clear, right? I have discussed with Markovnikov rule. Then in the next step, what happened when we add the peroxide with sodium hydroxide, H2O2 and sodium peroxide formation takes place, right? And this sodium peroxide will attack on BH2. So the lone pair of the oxygen will attack on boron to form the intermediate will looks like this one. So the deprotonated peroxide is more nucleophilic than the neutral peroxide, right? So here this is deprotonated in presence of sodium borohydride. That's why we have in presence of sodium hydroxide. So base, we are using base here to make it more reactive, right? After this one, the driving force for this rearrangement is the cleavage of oxygen-oxygen bond here. So rearrangement will take place. This oxygen-oxygen bond cleavage will take place, and this carbon will rearrange on this oxygen one to give the intermediate, which will looks like this one. Then this free OH minus will attack on boron, and O minus will generate over here. Okay. And then after the workup, it will take up the proton from water to give the alcohol, corresponding alcohol. So the alkoxide removes the proton from water to generate the neutral alcohol. So I hope the mechanism is clear to you. Thank you so much for your attention. I hope all of you understood the class, today's class, and all the questions related to these questions, this reducing agents. Let's quickly summarize the session, today's session. What we have discussed in today's class, we have discussed different reducing agents. So in case of the aldehyde, all the reducing agent can reduce it, which includes the lithium aluminum tetrahydride, sodium borohydride, dry nickel, palladium charcoal, double H, right? And we have discussed that ketone also could be reduced by all the other reducing agent. But in case of the ester can only be reduced by lithium aluminum hydride or ALH3, or it can also be reduced by double H, but at high temperature to alcohol. At lower temperature it will give the aldehyde. Okay. Then we have discussed that the acid functional group could be reduced by BH3, or it can also be reduced by the lithium aluminum hydride and double H. Double H and LAH can reduce all the functional group, but double H at different temperature giving a different outcome. Okay, different outcome. In case of acid chloride can be reduced by both LAH, sodium borohydride, and double H. But Rane nickel and palladium charcoal are ineffective in all these cases in case of acid, ester, acid chloride. Okay, palladium charcoal is mainly known for reduction of double bond, where the Raney nickel is used to reducing the some specific reduction, not the ester, acid and acid chloride. We have discussed in short these things. Then we'll move to the next question. We have discussed here already this one. So the question was predict the product of the following reaction, and we have discussed that the Markovnikov rule will follow here and carbocation formation will take place. So here chances of carbocation formation is there in those two places. But because both are secondary carbon, so it will give the same result. So that both the carbocation formation will take place here. After the carbocation formation, the coming nucleophile, which is Br minus, can trap the carbocation from the top side also and from the bottom side also on each of the intermediate. So if in first intermediate, this one is second one, it can approach by top side also and bottom side also, which will give these two products, right? But if it will approach this carbocation, which is also secondary carbocation, from the top side and bottom side, it will give these two products. So that's why the ratio of these products are 1:1:1:1. I have already discussed with chair confirmation why we will get all the different types of product. Here steric hindrance will not work. Then we have discussed here that if the tertiary carbocation formation will take place, suppose we have this carbocation formation which is at alpha position, then the hydride transfer will take place. And hydride transfer will give the tertiary carbocation formation, which will give you a only single product because of only one stereo center. So that's why the bromine ion will grab this carbocation to give the single product, that is no DR. That is no DR. Okay, single product. Then we have discussed the next question where we have slight change in question and the result is on distillation center. In this case, again, carbocation for stability will decide the